Introduction. Light is a form of energy and it causes the sensation of vision. With the help of light only, we see the beautiful and wonderful world. When a light falls on any object, that object reflects the light. That reflected light reaches the retina of our eyes. Then only we see the objects. We have learned about shadows and we carried out many experiments with light rays and also discussed the rectilinear propagation of light, that is, light travels in a straight line. And also we learned the laws of reflection. Let us recall some of them. A source of light, an opaque object, and a screen are needed to form a shadow. Light travels in a straight line. When light gets reflected from a surface, the angle of reflection is equal to the angle of incidence. The incident ray, the normal at the point of incidence, and the reflected ray all lie in the same plane. You must have observed shadows and images in your daily life. Some questions might have come to your mind while observing these shadows or images. Why does our image appear thin or bulked out? In some mirrors, why is there right-left inversions? When we look into a mirror, can we focus sunlight at a point using a mirror instead of magnifying glass? Why is the angle of reflection equal to the angle of incidence when a light ray gets reflected from a surface? Are the angle of reflection and angle of incidence also equal for reflection by curved surfaces? Light is having the property of reflection. Let's know about the reflection of light in detail, so we can answer any question. Finding the normal to a curved surface. Take a small piece of thin foam or rubber. Put some pins along a straight line on the foam as shown. All these pins are perpendicular to the plane of foam. If the foam is considered as a mirror, each pin would represent the normal at that point. Any ray incident at the point where the pin makes contact with the surface will reflect with the same angle as the incident ray made with the pin normal. Now bend the foam piece inwards as shown. What happens to the pins? They still represent the normal at various points, but you will notice that all the pins tend to converge at a point. If we bend the foam piece outwards, we will see that the pins seem to move away from each other, or in other words, they diverge as shown. This gives an idea of what is likely to happen with the spherical mirror. There are two types of spherical mirrors. Concave mirror. A concave mirror will be like the rubber roll bent inward, and the convex mirror will be like a rubber roll bent outward. Concave mirror is a part of a hollow glass sphere whose reflecting surface is concave. Such a mirror is called a concave mirror. Convex mirror. A part of a hollow glass sphere whose reflecting surface is convex is called a convex mirror. For a concave mirror, like their pins, all normal will converge towards a point. This point is called center of curvature E of a mirror. Recall a little bit of geometry. While learning about circles, the tangents You may have learnt that a radius is always perpendicular to the tangent to the circle diagram at the point. This gives us a clue about how we can find normal to any point on the spherical mirror, concave mirror. If we extend the spherical surface, a sphere is formed. That is, having center is called center of curvature of that mirror. Pole. The midpoint of a mirror is called pole. The line joining the pole and center of curvature of a mirror is radius of curvature. The line drawn from C to any point on the mirror gives the normal at that point for the ray R. The incident angle is the angle maybe the ray with normal as I, and reflected angle is shown. From first law of reflection, Li equals to Lr. Using the construction method described above, try to construct different reflected rays for an array of rays that are parallel to the principal axis. What is your conclusion? To verify this, we must first find out some way of obtaining a beam of parallel rays. How do we do this? Take a cardboard or a thermocol blocks, fix the two pins on the sheet. The pins are parallel to each other. Take a source of light as a candle. When a candle is kept near the sheet, the back of the sheet will observe the shadows of pins. We see that these shadows are diverging. Now, the position of source is moved or changed. What happens? We observe that the source is moved away from the pins. The angle of divergence gets reduced. That means we move the source far away, we will get a parallel shadows. But the source is far away from pins. As a result, the intensity of light becomes low. That means to get the parallel beam of ray, the source should be very far away from the pins and having more intensity. Where do we find such a source is observed in our nature. That is, sun. This is the natural source of heat and light, is a luminous body which emits the light with their own, very far away from the earth. So, such rays coming from sun are taken as a parallel beam. Let us do an experiment with sun rays and a concave mirror. Activity. Take a concave mirror, hold the concave mirror in such a way that sunlight falls on it. Place a paper in front of the reflecting surface of a concave mirror. We are slightly moving the paper and we find out a brightest part, which will be the image of the sun. Try to represent in a ray diagram. It is observed that the rays coming from the sun are parallel beam of rays falling on the mirror. The mirror reflects the light rays. These reflected light rays converge at a point on front of a mirror. At that point, the image of an object is formed. That means the reflected rays converge at a point of a concave mirror. That point is called focal point or focus of a concave mirror. It is again observed that the distance from place to the spot of a mirror is equal to the distance from that spot to center C. The distance between poles to focus is called a focal length. Radius of curvature will be twice that distance from spot to pole. So R equals to 2F. Does this help to verify conclusion of withdrawing that raised? If we change the position of the paper, we observe that if any object is placed in front of a concave mirror and the position of object is changed, that if it moves towards the mirror, then we are not observing the brightest spot on a paper. If we change the position of paper, the paper is moved through a distance less than focal length image of an object keeps on becoming small beyond the focal point. It keeps on becoming enlarged. Likewise, the image of the sun becomes smaller or bigger depending on the position of paper. Note: while drawing a ray diagram, it is not clearly mentioned the reflecting side of a mirror. The non-reflecting surface is represented as lines on that side. Can you draw the same diagram for convex mirror like a concave mirror? It is a mirror, a part concave mirror of a hollow sphere whose reflecting surface is convex is called convex spherical mirror. The parallel beam of rays falling on a convex mirror, the reflected rays reflected by convex mirror. It is observed that reflected rays appear to diverge after reflection. If we extend back these reflecting rays, they will meet at positive, or that is focus of the convex mirror. Note: a parallel beam of rays falling on mirror, that is concave, they converge a focus, the reflected ray really converging. So, the mirror is called a converging mirror. In case of convex mirror, a parallel beam of light falling on mirror, they diverge together. That mirror is called a diverging mirror. A set of parallel rays are falling on a mirror of convex. What conclusions are you drawn from this? The reflected rays are not converging. They diverge and not really meet at a point. If we extend back, these light rays appear to converge at a point. Will you get a point image if you place a paper at a focus? No, we will not get a sharp image on paper because the reflected rays are not really meet. Then the formed image is virtual image. Virtual image cannot obtain on screen.